Our next speaker is Takashi Kimura. It's titled Orderable Operations Equivariant Case.
Thanks very much. All right, so anyway, that's the title, that's what I am. And so what is this? It's a 20-minute talk, you know, you gotta go. So there we go. So just from the outset, I was just some fine print that I'd like to remember throughout the talk about a smooth complex value scheme. I have a closed subset of GLNG acting on it, and then actually it's probably I take a dice stroke of this time. And in general, I'm going to assume that the groups and rings that show up will be over two coefficients, but that's just because I'm lazy for the most part. I'll indicate when that's essential as they go along. So the main thing I want to talk about is the following: if you start with ordinary equivariant K theory of X, you have some ring, right? And you also have a corresponding Chow theory or Kolmogorov theory, right? You have rings there as well. And then there's a Chern vector map from one to the other, which indeed preserves the multiplication of the ring homomorphism. So that's well known. So what I want to talk about are sort of more exotic versions of this and more. So these are subrings inside something else. Right? In fact, maybe I should say this here. So these are subrings inside some more exotic kind of homomorphism. So there's this space called IX, which is the inertia value of X. I'll tell you what you think about later. Has an active group. And of course, this thing is also an equivariant K-theory from a product. But I'm going to put an exotic product on this equivariant K-theory and this equivariant Chow or Kolmogorov. And so these exotic products are really in the matter of the Chen and the Wan. Basically, they did their construction in homology. Programmers said that this did this basically in Chow, but it's really the same idea. And other one describes the same thing in K-theory, but again, same idea, really, Chen and Wan. And then with Jarvis-Bukowski, we formulated this definition in an alternate way, which doesn't involve any complex curves that will be essential in what follows. So I'm going to use this alternate description, but it's fully equivalent to the original Chen and Wan. Okay, so in this theory, there's a commutative ring structure here, and there's a commutative ring structure here, and there's an exotic ring homomorphism that preserves this exotic product structure in such a way that these include the subrings. So I should just say that. So that, of course, what we did here, I should also mention this work. So the stuff I'll talk about today is work in progress with Edwin and Jarvis. And in fact, we did an earlier paper where we talk about this case in some detail as well. So I should also mention some physics as well, because of course this theory is a fact of physics. Right? This is really some sort of untwisted sector inside this sort of whole theory. Going this way. And physical theory, the work of Rafa and Nato is going to be most relevant to this particular theory that I'm describing. Although you talk about homology. All right. So the question I would like to ask is, K-theory has additional structures on it. Right? It has this weird application on. So ordinary K-theory has, it has a product on it. It also has a structure of something called a lambda ring or psi ring, which I'll explain. And it has Chern classes and Chern characters and so on. And these things are suitably compatible. So the question I'd like to try to pose and answer to some extent is when can you generalize these things to this more exotic type? In such a way that when you restrict to sort of the untwisted set, you recover all the class operations. So let's just recall what I mean by this structure. So what is equivariant K-theory, right? I mean, we're really talking about a ring from the outset, right? So I'm talking about the Duffy group of complex vector bundles that are G-equivariant. And that's a ring, right, with multiplication, where it has an equivalent isomorphism class of vector bundles by multiplying by using the tensor product. And that's a community multiplication, which is here. So what's a lambda? lambda ring? Well, the lambda ring structure is basically the following. So we have a map now. So for any element in equivariant K-theory, you now associate a power series in P with coefficients in that equivariant K-theory. So in the following way, parameter T is a formal parameter. And so what is a pretty easy thing to understand? It's because of power series, it's I lambda power of this isomorphism class of vector bundle is just the I third power. So in particular, if you see the class of vector bundle here, it's a polynomial, right? The rank of. But more generally, the elements in K-theory we differentiate. So if I'm working with Q coefficients, the linear combinations of vector bundles become coefficients. And so I just want to extend this to multiplicity. So if I have a sum becomes a product, and then these coefficients will become exponential. So the power series in P, for example, if this is -1 or a half or something, so you're extending 1 plus polynomial 1 plus higher order terms in P with some fractional or inverse power. So we use that all the time. Okay. So there we go. So this is called lambda structure. And so why do I care about this thing? Well, there are various reasons I might care about this, but the one very easy thing to explain is the fact that if you talk about the K-theory of Euler class of vector bundle, you take the dual vector bundle where you plug in T equals -1, and this thing is Euler class. So you're doing Euler class. Notice that the sum here is finite, right? Because this is a vector bundle. That's why they take the Euler class of sum. This formal difference of elements here really makes sense. Okay, good. So let me just formalize that structure, right? So the structure here is called a lambda ring. So that thing, of course, this K group here, that's the K group on the bottom. This is something called a lambda ring. And a lambda ring is just, well, that means that lambda operation that I defined earlier satisfies a bunch of properties, right? So I is a commutative ring, and then these operations satisfy some properties. Okay, and so this is maybe the most important one, right? So the multiplicity. And this is like basically so for the structure sheet. These polynomials here are some universal polynomials that exist. If you want to derive what, I can't remember exactly what they are, but they're easy to derive if you sort of remember the splitting principle. You can actually derive what this here. Okay, so anyway, there's something called a lambda ring, and this K group with this structure. Okay, so that's an important part of K-theory. And so part of the things that I'd like to understand is if I can extend that lambda ring structure somehow to this more exotic orbital K-theory. Okay, so in order to do that, I have to actually introduce an auxiliary thing called the psi ring. Okay, so the lambda ring operation is very closely related to something called the psi ring operation. And so what are these psi? Okay, so you have now that same ring, you have a commutative associated ring with you. And you now have a collection of operations indexed by n, where n is equal to 1, we call them psi, and they satisfy some properties. Right? So the first psi is identity, these psi n's are each ring homomorphisms, which is an application, and they have this property that if I compose psi n and psi n, this psi is a funny thing, and so this is what we call psi ring. Okay, so why do I bring in this sort of third party? Well, it's actually the psi rings that are sort of central to what we'll do. And the relationship between psi rings and lambda rings is normally the following. So let's see here. So if you have this commutative ring, and let's take this formula here. Right? So suppose A is an element of that ring, and this is a formal power series in P, and this is a formal power series in P, where exponentials is equal power series for exponential. And we can compare term by term in P, and you get some relations between the psi and the lambda operator. Right? So if you start with a psi ring, so if you start with a lambda ring, and you define the psi through this formula, then you'll get a psi ring. Right? On the other hand, if you start with a psi ring, and then you define a lambda this way, you'll get a lambda ring provided that you're over Q. So this is one place where Q is okay. So the point is that the equivariant K-theory is in fact a psi ring. And that psi ring operation is part of the line bundle, which is n power the splitting principle of this convention. Okay. So these types of Q, these are equivalent. whole theater. So what is the whole theater? So
in all these stories, R has to be commutative, right?
Yeah.
Will the K theory of the inertial space be commutative?
Sure.
What about the case when the vector bundle is not aligned though?
Right, it's splitting principle. But you can also define it through that formula as well.
So this corresponds to taking tangent with itself?
Yes, that's what it means. Sometimes we call that as well. Okay, so if I have this space S, I define this new space called IX, called the inertia of X. This is just a pair of root bound and point, and that is fixed. So G acts on that pair diagonally, where G acts on this vector by conjugation of two times. Called the inertia variety of X. The inertia variety of X contains breaks up naturally into pieces indexed by conjugacy classes, because those graphs answer belong to conjugacy classes. So I can write it like this. So G bar is a set of conjugacy classes. And then associated every conjugacy class, you have what we'll call I to phi of X for every conjugacy class. Right? So it's a set of all things where this thing belongs to that conjugacy class. Those are all G spaces. And in particular, I'll just call X to the n to be the set of all pairs in the inertia here, such that the root element on the left side is n. So properties implies that basically that the sum here is finite, and the order of the conjugacy classes is finite. To ensure that we'll need that crucially when it follows. Okay. All right. So now we have to define the K-term. So there we go. So why is this? Well, it's really the G equivariant. If you look at the last line here, sorry, I'm really looking at the G equivariant K theory as a thing. But the G equivariant K theory you can equivalently write in this way, where Z is the centralized set of subgroup elements in J that can move that. And so we're really talking about this thing as an additive. Right? So we don't use the product that comes on the tree. And you can do the same thing in cohomology and Chow as well. And so now we're going to define the product. And I'm using a description that was due to that we did at the paper with compound and also with additive. So what we do is we define this mysterious object F in the K theory of inertia in the following way. So we consider the object tau, which is a tangent bundle on X. We subtract the V algebraic from that. And so then, so now we consider S in the following way. We take the tangent bundle here and restrict it to the inertia, where the left factor is n. And so you can think about this as a set of points inside X that are point-wise fixed by n. So then you can break up the tangent bundle into eigenbundles of that action, indexed by k, which take us from 0 to the order of n. And then you weight, you take the sum, but now you weight it by the log of that eigenbundle. And the significance of this in some sense is the age, so to speak, or the rank of this thing. Some sort of K-theory age. The age is something we've seen before. This is no extraordinary, nothing this is before. Okay, so in order to define the multiplication, we need to do something called a double inertia. But just I'll just sort of, for reach of time, cut down here. There's something called a n vector is really the pair M1 and 2 two-group elements. And so the double inertia, therefore, is a triple. Two group elements in X, such that N1 fixes X and N2 fixes X together. Okay, so now the multiplication can be defined as follows. The multiplication is defined by this. Okay, so if I take two elements and take their here, I can pull them back here, right, because to this space here, and then I can push forward via multiplication. So, and then I pull back, I multiply them, and then I can couple with some Euler class of some object. And this object here is constructed from those vectors. So the miracle is somehow this thing here is in fact represented by a vector bundle, something that's not obvious here, but in fact is an instruction multiplication. That's the kind of about the okay, so this makes sense. And then
it's the same as a one defined by time as alpha right?
It's equivalent, of course. But the formulas are, of course, it's equal to the K-theory two-dir class. But the point is, I guess, is that formula for us will be crucial because we'll need that S in our formula. Yeah. So, of course, this is non-negative. So, indeed, right? So, therefore, this is going to be a commutative ring. This Chow homologous is a commutative ring. These things agree with the sort of orbifold shadow rings and orbifold chronologies, the Chen and Guan is well defined. And indeed, there's a string character, and this is the most interesting part. There's a string character map here. Because there's a dot multiplication, there's a correction by the top class of that S to show up. So the formula that we wrote down, that we use for the obstruction model, we try to carry an S, and that S is crucial in making sure that the product is on a set. Okay, so I should say that, so let me just explain with the firing, how to fix up the size of this thing. There's something called a bot class. So for every integer j, if I take a line bundle like L, and I provide a bot class, I define it as the sum of those countries. Okay, for every j bigger than equal to 1, and then I can use the splitting principle and extend this thing to multiplicity of class to get a vector bundle. And so we just consider this formula. It's an ordinary psi operation, and then we multiply by the correction from bot class. So now, I claim that this is a psi ring. This gives a psi ring operation on the orbifold K theory, or at least a part of orbifold K theory. So notice the swiddle here, on which this bot class makes sense. Okay, so I don't have much time, but so there are some cases where in fact it's defined on the entire K theory, and because the bot class will make sense on the entire K theory, sometimes it will only be defined on sub rings of K theory. It's also always defined on certain localization with respect to orientation ideal, which I won't be able to say much about. So how could this thing fail to make sense? Well, remember, if it were like half a line bundle, imagine we take from theta j half a line bundle, that would be like theta j L to the 1/2. If you try to extend that out, you get infinite series. So it can fail to make sense if the S here is not represented by vector. Or if you don't overlap. Okay, so that's the thing. Is that there's this thing, some subring, which I have time to explain precisely now. So it's exciting selection on the subring of local figures or on certain localization. And therefore, lambda ring structure is what we do. There are also orbifold string classes. So we talked about orbifold string characters. You can also define some notion of orbifold string classes, where there's a string character and string classes, right? And these psi's and lambdas, they satisfy some compatibility relations in this orbifold setting, a generalized visual ones. There's also a notion of dualization here, in the sense that simply rules of vector bundles, and the orbifold notion of that, which we also have to correct the notion of taking rules. Weirdly, I also like that. And finally, these are all the orbifold products one can write down. See with the formula that we wrote down with S's, you can replace S's by some other S's, it's still the associated products. As in, for example, the spiritual orbifold homology, the Takashi Kimura and this person came right out how to pronounce all these statements will also work there if you use their S's. And the merit of this theory here is that the S's in that case are always vector bundles. Right. Well, so if you do the K-theoretic version here, right?
Yeah, but you just wait on the coordinate.
Well, if you think about that, well, we can talk about this later. There's some subtlety. Yeah, I know what you mean. But that has some merits because the S is there to manifest the objects and then the operations are defined. Okay, so that's one whole minute left. Wow, how did that happen? Okay. Maybe I can just I guess I'll make it a little bit. Okay. So maybe I can adjust this a little bit. Right? So if you think in terms of vector bank K-theory, it's I think in vector bank K-theory it's not quite. If you're keeping track of the group action, I'm not sure that it's exactly the same as this cosine function. Yeah, there's a little bit of a trouble. So just to explain what those guys do, right, there's some kind of normal bundle, right, of these fixed points of X by group element n inside X. And if I just find the X's in my earlier formula, so basically you get normal bundle. Instead of my earlier definition, you get a new problem, a different problem. In fact, if you write down tons and tons of orbifold products, you see you name anything. This is the second one. You write down 4. It's very easy. And so any one of those guys, these constructions will work. This is very robust stuff. And it's always from that from the discussion. Thank you very much.
Quick question? So you have these, you have generalizations of possible
term numbers, just more topics.
Right. But there's one thing I haven't answered yet, which is what is a vector bubble?
Right.
And you have a lambda ring, right? So how do you tell it gives some random K-theory class, and you want to know whether or not that K-theory class is a vector bubble. One test is you see if it's lambda series is polynomial. Then there's a chance that it's a vector bubble. Right? Here, what's the overflow notion of vector bubble? It's not so immediately clear, but I could certainly talk about elements here whose lambda series are polynomial, and then I could talk about these kinds of things, a lot of these kinds of things. More generally, it might be a little bit clearer. There's some examples where that I'll tell you later.
So in the algebraic context, the Stern character map from the usual space is nowhere near surjective onto cohomology. Do you have any version of this that would, algebraic K-theory only maps into a very small part of the cohomology, but Hochschild cohomology, which is the slightly spruce version. Hochschild homology, which is a slightly spruce version of K-theory, does map surjectively onto. I've been hoping for 15 years to find a product formula for Hochschild cohomology of an orbital.
I kind of wanted that, something like that for a long time. I see what you're saying. So it's surjective, but is it an isomorphism?
Yes, it's an isomorphism.
So if you pull back, I think you could in theory have some.
Yeah, and you have operations like push forward and pull back and things of that sort.
And there's a natural map from this Hochschild thing.
Yeah.
So then you definitely have a product. It'd be really interesting to see that.
Yeah, the only question is what is the there is a naturally defined product on Hochschild homology, and it's not clear.
Does it have this kind of twisted set?
Yes, absolutely.